Hello everyone, welcome to Technologies Discussion Channel. Today, I'd like to continue the discussion on EMC consideration. On my previous discussion on the Part 68 series discussion, I have discussed how can we actually perform conductor immunity using this CDM, coupling decoupling network. So basically this video, I will explain the procedure, how can we actually perform another so-called method of testing CI, which is the electromagnetic clamp. Okay, so basically this electromagnetic clamp is also known as current injection. So basically this video with the other previous one, you will be able to distinguish the key difference between these two types of testing for conductor immunity. So this will be the objective of these two set of discussion. This will be the part 69 series discussion on EMC. So guys, if you're keen to know more about EMC, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion on EMC. This is my email. If you have any question regards on this discussion, okay, please drop me an email. Okay, or if not, if you want to have a faster response, you are always welcome to ask me through the comment. Before I continue, I'd like to urge you guys to help this channel by pressing the like button. Okay, so when more of you guys actually help me to press the like button, this video will have a better chances to reach up to a larger audience. So guys, help me press the like button now. For those who are new to this channel, please consider to subscribe and turn on your notification bell. Once again, thank you so much for your strong support. Let's quickly understand what is conductor immunity. Okay, so the conductor immunity test is a very common EMC test that is actually required, for example, for commercial, the automotive, and maybe supporting the military. Okay, whether you build a new equipment, whether you build a new product. So basically, this EMC test, which is conductor immunity, is a very common test that you need to do, okay, for all these products here. The testing requirement, the frequency range, the setup, and also the required test equipment, they actually varies, and it actually depends what standard you actually want to test, and also what will be the test level. Then all these different setup, different equipment, different frequency, etc., will be changed accordingly. According to the standard IEC 61000-4-6, they actually allow three different injection methods. However, the first method, which is the CDN, is always the preferred one. So if you are able to perform your CI using this CDN, so please go ahead to use this CDN method. If not, then you move on to the second method, which is the electromagnetic clamp. Okay, so basically this video, I will explain a little bit more on this electromagnetic clamp. And then if I'm not able to use this EM clamp, then I will use this direct injection. So in short, the first priority is always CDN, followed by electromagnetic clamp, and last but not least, use this direct injection. So basically, this is what the standard call for. Okay, so it actually explained over here. The preferred method is always using a CDN, as these are designed for testing specific cable types. Depending on the equipment under the test, multiple CDM may be required if we have multiple ports or connection that need to be tested. Okay, the figure on the next slide in the selection guide will actually provide some rules for us to select the injection method. Okay, so this is actually the flow chart. As I mentioned earlier on, CDN is always the first consideration. Okay, so basically the first consideration you will ask yourself whether CDN is applicable. So it's yes or no. So what kind of cable then it will be applicable for CDN? Mainly for power cable. So basically for CDN, you actually have a special design CDN to test the power cable. And also on the shield cable, for example, the coaxial cable and some screen data cables, you can also test using the CDN. The unshield twist pair or maybe the data cables, okay, for example, the internet CAN bus, etc., you can also consider to use CDN to test it. We also have the unshield power cable or control cable. So in short, okay, earlier on I did mention about coaxial cable. Okay, for example, we can test the RF cable, okay, and also various form of communication lines. Okay, so basically these are the few possible that we will use this CDN to test the conductor immunity. So if under a certain situation where this CDN is not applicable, then we will move to the right, which is no. Then again, we will ask ourselves whether is it a screen cable. If it's yes, then we will use this EM clamp to do the test. If it's no, then we will fall onto the right. Let's take a look on this so-called yes, that using this EM clamp to test the conductor immunity. So if this is possible, okay, why or what types of cable is possible? Okay, it's the same thing. Okay, for example, the power cable, whether it's AC or DC. Okay, so basically from here, I highlight the DC cable that will be test, okay, using this EM clamp. Okay, so shield cable, okay, that is mainly used for high-speed data communication or control signal, which is not available, okay, for the CDN. Okay, remember for CDN, we actually has a set of so-called unique design CDN device to test that. So those that don't have will actually fall into this category here. Next, we have the unshielded cable. Okay, commonly we use this in automotive and industry application here. Okay, all this can be also used under the EM clamp. Okay, for example, you have some proprietary cable, etc. Then you can also use this EM clamp to test. Okay, over here, the last one will be communication and control cables here. Okay, for example, RS232, RS485, I2C, SPI, etc. So these are all the industry control line that you can use this EM clamp to test it. Okay, so let's move on. Okay, so the EM clamp are RF current injection clamp that use both inductive and capacitive coupling. Okay, so basically over here, must emphasize for EM clamp, we have both inductive and capacitive coupling, okay, to induce current onto the cable within the frequency range of 0.15 to 1000 megahertz. Okay, the term electromagnetic wave actually refers as the clamp simultaneously use of both inductive and capacitive coupling. I guess you know the meaning of electromagnetic. Okay, basically with the E field and also the magnetic field. So basically you need to have the inductive, okay, which is for the magnetic field, and you actually have the capacitive coupling, which is for the E field. Okay, so basically in short, EM, you actually need to have the both inductive and capacitive coupling here. One, let's discuss the benefit, okay, of using a EM clamp. Okay, I think the clear benefit is basically this, which is the non-invasive. Okay, so for EM clamp, you actually has the key advantage of non-invasive. Okay, so unlike direct injection method, the EM clamp does not require us to break into the conductor of cable. Okay, which means that we don't need to cut the conductor. Okay, so the noise will actually couple over to the conductor of the cable. Okay, so this actually allowed for easier testing on existing system. Okay, so therefore we don't need to break our connection. So hence this method is so-called the non-invasive, which means that we don't need to cut the conductor in order to so-called test this under the CI. And also another advantage is wide frequency range. Okay, EM clamp actually operate across a very broad frequency spectrum, okay, which make them very suitable for testing on the various standard. Okay, because different standard, the frequency range also vary. So hence, probably EM clamp will be the better one because they can specify a wide frequency range. Flexible, okay, again, you can imagine that if we can just couple the noise over without breaking the joint. So therefore, you have the flexibility, and this can be actually applied to many different types of cable types and also different configuration. Okay, so this quickly explain the key benefit when we actually use this EM clamp as conductor immunity. Come to the construction of the clamp. Okay, the EM clamp actually consists of two set of right ring core. Okay, so what are these? Okay, so basically this is the picture of EM clamp. You can see over here, this is the one set of right core. There will be another one over here. So basically you can see that we actually has two set of right ring core. Basically they are connected by a hinges. Okay, over here you can see that there are actually three hinges. Okay, so basically you imagine that this thing can open and close. Okay, using the latch over here to do the opening and close. You put your wire, okay, along the EM clamp that is over here, and this thing you can cover, and then you actually so-called latch it. Okay, so this is what it mean here. In addition to the ferrite containing device, there is also a metal cable or rod that aid in connection during calibration and verification of the clamp characteristics. Okay, so basically you have a rod over here. So this rod actually simulate like your cable, your conductor of the cable, and then after that, this will be mainly used just for calibration only. So imagine this, okay, because we need to do calibration, okay, this rod actually is placed in between this ferrite core and then basically the energy couple from the ferrite core all the way to the conductor. Okay, so basically from there we will be able to eliminate how much so-called volt per meter is actually coupled over. Okay, so this is what is said over here. Okay, during calibration, the figure below illustrates the main component of the clamp, including the ferrite in both sections, which I have just explained. Okay, another key thing is there will be heat sink over here and some ground connection. Okay, so we will come to this later on. Okay, so this diagram here, okay, actually is the calibration setup. Okay, for this method, okay, when we actually conduct immunity using this EM clamp, before you can actually test, you actually need to do a calibration. Okay, why we need to do calibration? This is to ensure, okay, the correct amount of so-called EM wave is actually coupled to the conductor of the cable. So hence, because of this, we need to do a calibration before we can actually do the testing. However, if you have saved your calibrate result, it's also okay. So you just need to rerun your calibration result to facilitate the test. Okay, but over here, I like to have a complete discussion. So let me so-called describe how does the calibration can be done, okay, with this EM clamp here. Okay, so there are actually two diagrams. The first diagram here, and this is the second diagram. Okay, I like to emphasize a little bit on the second diagram first. Okay, on the right, you can see that there are actually two set of solution. The first set of solution is the EUT. Okay, so basically the top one is actually for the testing of the EUT, while the bottom one is mainly for calibration. So basically, when you actually do this for calibration, it will be route to this path here. And when you actually do it for testing, then you will route to this path. So doesn't mean that these two things exist simultaneously. Either one will appear. For testing will be this configuration. For calibration will be this configuration. Okay, let's go through in deep detail here. So this is actually a signal generator. So they basically generate the signal or the noise. So they actually generate the noise. So this is the output of the signal generator. They come out over here. So in this diagram here, this is actually the signal generator. So the signal generator actually generate up the signal. The first thing they actually go through this 6 dB antennator. Same over here, they go through the 6 dB antennator. Later on, I explain why we need to have this 6 dB antennator. Okay, so in short, they actually prevent saturation. But over here, you can see that after they go through the 6 dB so-called antennator, they will go through the whole ferrite core over here. So in short, you just imagine this. They go through the 6 dB antennator, then they will go through the whole ferrite core and reach out over here. So when they reach out over here, let's say this is for the calibration, then you have this set of equipment. We have this 100 ohms of adapter, which you can see over here. We have this 100 ohm of adapter here. This is 50 ohm. Okay, the equipment, okay, or the signal generator over here is actually 50 ohm. So basically you can see over here, this is to do the monitoring. Okay, so basically this is to do the monitoring. And then after that, you can see on the left-hand side over here, this is where we put our power source. Let's say we are doing the power source testing. We actually supply the power source to power up the EUT, for example. And over here, if let's say we do the calibration, okay, we need to ensure that the power source will be here. Okay, we need to ensure that the signal actually coupled towards the EUT rather than to the auxiliary. So later on, I will explain this. Okay, so basically this is the setup when we actually want to do the calibration. You can see in simple signal generator with a 6 dB antennator, they are fit into one side of the EM clamp. And then basically over here, you just imagine the signal actually will couple from all this range onto the cable. And this will be the side that you actually connect your EUT. Okay, so basically the EUT need to be 150 ohm, which later on I will explain why 150 ohm. Basically, you can see that 100 ohm plus 50 ohm, which is 150 ohm. Okay, so basically this is the setup for calibration. Okay, let's quickly move on to the so-called testing setup here. So this is for the test setup over here. Okay, it's quite similar what we have discussed earlier on the calibration. So the signal generator generate the noise Okay, so basically, again, they will pass through the 6 dB antennator. This will be over this path here, and the thing will be so-called moving through the whole ferrite core over here. So now it's basically for the EUT, so the noise actually will couple into this path. Majority of the signal will be coupled over this path to disturb your DUT. And from what our observation, we see our EUT can function or not. Okay, so basically over here, you can see that we have something that break the EM clamp and the EUT is basically we call this as a monitoring probe. So basically the monitoring probe will ensure whatever food that we need to so-called add as a noise source that is actually disturb the EUT over here. And again, for example, for this case here, let's say we are doing the power monitoring. Okay, so basically we will supply the power source to power up your EUT, and the noise actually couple from the signal generator all the way towards the direction of EUT. Very little amount of so-called EM wave supposed to reach the auxiliary, because this part we are not testing. We are only testing our EUT. So we need to ensure this part here. So most of the case, okay, so basically the EM wave is actually very directive. They actually will focus on a specific direction, which is towards the EUT. Okay, so basically this is how we actually do this EM clamp, okay, for this conductor immunity. Okay, so before I continue, if you have learned something from this video, okay, please help me to like this video and subscribe to this channel if you are new. Okay, so also please help me to turn on your notification bell. Once again, thank you so much for strong support. Now let me quickly explain why 150 ohm. Okay, I have couple of email that ask me, okay, why it need to be 150 ohm. Okay, so I take this opportunity to describe why we need to have 150 ohm. Okay, which is this part here. Why 150 ohm here? So basically for this part, okay, for this part here, why 150 ohm? Okay, so let me explain. Okay, in conductor immunity testing, okay, with an injection clamp, okay, which is EM clamp, achieving 150 ohm at the equipment under test port is critical for standard compliant and accurate result. Okay, so in short, because of the standard, okay, it actually require the EUT ports is basically 150 ohm. So basically, they want it to be so-called compliant and accurate. They want the so-called the result to be consistent. So hence they specify this 150 ohm. Okay, so the standard compliant, okay, so basically the IEC 61000-4 state standard actually mandate a 150 ohm common mode impedance at the EUT port so as to ensure repeatability and also consistent when we actually do this test RF in immunity test here. Okay, so this apply to conductor disturbance induced by RF field in the 150 kilohertz to 230 megahertz range here. Okay, so the next reason is because of the simulation of real world condition. Okay, the 150 ohm impedance represent the typical common mode impedance of cable in a practical installation. Okay, so another reason is because most of the cable in practical installation, they are actually 150 ohm. So basically we want to simulate as a real world so-called condition having this 150 ohm impedance. Okay, so it also approximate the impedance of power or signal cable that is actually connected to the EUT in a real-world electromagnetic environment. Okay, so this is the second reason why need to be 150 ohm. Okay, let's come to another three more. Okay, so one will be the proper power transfer from the clamp. Okay, the injection clamp actually induce the RF signal into the cable. Okay, but power transfer efficient depend on impedance matching. Again, okay, because of the impedance matching, we need to match it 150 ohm to 150 ohm. So hence, we need to ensure proper power transfer or maybe maximum power transfer from the clamp. So hence, okay, we need to ensure compatibility because of impedance matching. So hence, is also another reason why the EUT port need to be 150 ohms. Okay, so if the impedance at the EUT port actually deviate too much from 150 ohm, the applied test level may not be accurate anymore. This may be led to under or over testing of the EUT. Okay, no, next reason is to ensure the correct stress on the EUT. Conductor immunity test actually verify whether the EUT can still function, okay, under this EM stress. Okay, significant impedance deviation can alter the voltage and current applied to the EUT, and hence they will be compromised the test validate. Okay, so in short, okay, we need to ensure 150 ohm so that the result can be consistent. use of a CDN or impedance stabilization network ISN. Okay, so a coupling decoupling network or an ISN is often used to maintain a stable 150 ohm impedance, particularly for the wire interface. Okay, when using an injection clamp without a CDN, a 150 ohm termination at the EUT port ensure the correct test condition. Okay, so basically this is the 5 reasons, okay, why the impedance need to be 150 ohm. Okay, so let's move on. Let's come a little bit more discussion on the test itself. Okay, the signal from the signal generator is introduced through a single turn loop that run the length of the clamp from one end to the other. Okay, so basically this is what it means. Okay, earlier on I did mention that the signal gen actually generate a signal. So they pass through the 6 dB antennator and they basically run through the whole length of the clamp from one end to the other end. Okay, so basically you can imagine that this will be the source of coupling. The noise actually generate from here, couple over to the conductor of the cables. Okay, so and is terminate with an impedance at each end of the clamp terminal. Okay, this actually create a voltage. Okay, so basically you actually create a voltage which provide capacitive coupling. Okay, so basically in order for the signal to travel, you need to have a voltage difference. And once you have a voltage difference, you actually generate capacitive coupling. And because of this, you actually also induce a current. Okay, so once you induce a current, this actually provide another coupling, which is the inductive coupling. Okay, so in short, because you need the signal to travel from one location to another location, so I need to have a potential difference. Once you have a potential difference, you actually will induce a capacitive coupling. And once we have this capacitive coupling, the coupling signal actually couple over to the conductor of the so-called cable, for example, for this case here, and therefore a current flow. So hence, when a current flow, you actually also induce the inductive coupling. So over here, you can see that EM clamp actually has both the capacitive and also inductive coupling here. Okay, due to the combination of the graded ferrite and capacitive and inductive coupling, okay, the clamp actually exhibit significant directive, especially true when the frequency is above 10 megahertz. Remember, I told you earlier on, the test is to move towards the EUT rather than to the AE. So therefore, the signal must be directive. I want probably more than 90% actually travel towards the EUT rather than to the AE. So hence, because of this, okay, I need to ensure it is actually directive. So this is actually very directive, especially true when the frequency is more than 10 megahertz. Okay, as a result, a much lower signal is actually applied to the AE end of the cable, and the common mode impedance observed by the EUT remain close to 150 ohm across a large portion of the test signal spectrum. Okay, so this is the meaning here. Okay, majority of signal, I actually want to move it towards the EUT rather than to the AE. A consistent impedance may be achieved, okay, when we actually correct bond the EM clamp to the ground plane. Okay, so basically, if you need to ensure that, you need to ensure that they actually has a proper ground, as you can see from here. Okay, you can see that they actually need to have a proper ground so as to achieve, okay, consistent impedance of 150 ohm for this case here. However, deviation caused by the cable configuration on the AE side of the test setup, as well as those by the AE itself, are kept to a minimum. Okay, to maintain a stable output of BSWR generator, okay, which is the power amplifier. Okay, so we have the signal generator power amplifier. Okay, so basically they need to be antennated by 6 dB so as to ensure a stable output of BSWR. Despite this addition antennation, the coupling loss of the clamp is sufficient low, so it does not require significant more power than a CDN to achieve equivalent level. Okay, so basically, in short here, okay, so basically we generate all the noise source. The noise source are all here. They are actually so-called coupled onto the conductor of the cable, and then they will move towards the direction of the EUT. Okay, so basically this is why or how we actually do the conductor immunity using the EM clamp. Okay, so the setup for using EM clamp is especially important, okay, given the critical role of grounding in conductor RF immunity test. Okay, the image below illustrates the calibration setup. Okay, so basically this is a calibration setup. Okay, first thing we need is this signal generator, or we call the conductor RF test system. The second one will be the 100 ohm adapter. Okay, so this is the 100 ohm adapter. We also have the 6 dB antennator, okay, which is the third one. This is actually the 6 dB antennator. The fourth one is actually the EM test. Okay, so basically this is actually the EM test clamp here. We also have the 50 ohm termination load. Okay, so basically from here, you can see that we can terminate this as a 50 ohm termination load. We also have the calibration cable. Okay, so the calibration cable is not really shown over here, but you can see this so-called calibration cable. It can be a solid rod also, okay, or it can be also a calibration cable here. So basically, this show a very simple setup for calibration setup. Okay, so let's move on. Okay, the test before you actually can do the testing of the EUT, we need to calibrate first, as I illustrated earlier on. The test setup is first calibrate, and the test level are record. Okay, so the test is then performed based on the record test level. As with other test method in IEC 61000-4-6, okay, 150 ohm to 50 ohm adapter are actually used during calibration. Okay, let me explain the calibration. Okay, the figure below show a typical calibration test setup in according with this IEC 61000-4-6. In the figure, the necessary test equipment is integrated into a single test system, okay, which means that this is a single test system. As with other immunity tests, grounding is especially important. Okay, so hence it is critical that the calibration adapter have a solid connection to the ground reference plane. Otherwise, the calibration will fail. Okay, so basically in short over here, you probably can see this so-called solid black line. So this is actually the grounding plate. Okay, we need to ensure that they basically touch on the reference ground so as to ensure that we have this proper grounding. So this is how we need to ensure the calibration to be so-called accurate. Okay, so therefore we need to ensure a proper grounding first. Next, okay, once the calibration has been successfully complete, the setup will be adjusted for conductor test where the safe level will be applied. Okay, so this setup still include the 6 dB antennator output. As you can see here, this is the 6 dB antennator output and does not yet incorporate a monitoring probe or decoupling clamp. Okay, so during the actual test, the calibration adapter are removed from the setup. As you can see that there are no adapter anymore. Okay, so the purpose of ferrite decoupling clamp is to prevent the test signal applied to the intent cable from the affecting other device, equipment or system that are actually not under the test. So in short here, we actually couple the noise onto the cable, for example, for this case here. Okay, so there are two possibilities. Okay, the EM wave will definitely travel to the EUT. However, we cannot stop any EM wave from traveling towards the auxiliary equipment. Okay, so basically we want to ensure this. So therefore, we most of the time we actually can actually clamp this decoupling. Okay, so basically you imagine because there's no more space I can put over here, you can imagine that I actually can put this decoupling clamp over here. So basically they will remove most of the noise before it actually reach the auxiliary test here. Okay, so it also improve the reproductive of the result. Okay, so these clamps are commonly used when multiple lines are connected to the EUT and should not be exposed to interference. Okay, so basically this is what it means here. So we need to prevent this decoupling clamp. It actually so-called is actually supposed to be here. So they actually stop all the signal before it reach the auxiliary equipment. Okay, so in short, let's quickly go through the key step in the procedure. There are four of them. So firstly, we need to connect the EUT. Okay, we connect the cable of the EUT to the test system so as to ensure proper grounding. Okay, so I have emphasized how can we actually do a proper grounding. Next, attach the EM clamp. Okay, clamp the EM clamp onto the cable where you want to inject the RF signal, okay, typically near the EUT connection point. Okay, for example, your cable is very, very long. Make sure you clamp your so-called EM clamp that is near to the EUT. Okay, we don't need to clamp it near to the so-called auxiliary. Make sure that we actually clamp near the so-called the EUT. Next, okay, calibration. We need to calibrate the EM clamp and test system to ensure accurate signal injection level. Okay, coming to the signal source. Okay, so basically the signal source or the noise source is actually from the signal generator. Okay, so we need to connect the signal generator to the EM clamp. Okay, basically we set up the desired frequency and also the amplitude according to the test standard. Okay, so basically these are the essential thing that we need to do before we actually test the EUT. Okay, so next, okay, once the calibration is successfully complete, okay, the setup will be adjusted for conductor testing and the safe level will be applied. Okay, the setup still include the 6 dB antennator output, but does not incorporate a monitoring probe or decoupling clamp. Okay, during the actual test, the calibration adapter actually removed from the setup. So after you have do all the calibration, make sure you remove all the calibration adapter. Then we just need to hook up the EUT, okay, and also the signal generator with the 6 dB antennator. So once we are ready to do the test execution. Okay, so the first task is we sweep the frequency range. Okay, we gradually sweep the RF signal, okay, through the specific frequency range, inject the signal into the cable via the EM clamp. Next, we need to monitor the EUT response. Okay, while we inject the noise source, we need to closely monitor the EUT operation, okay, using appropriate measurement equipment, okay, to identify any malfunction or performance degradation. And last but not least, we need to record down the data. Okay, we record down the injection current level and we observe any abnormalities in the EUT behavior. Okay, so with this, I have so-called finished the discussion, okay, how we can actually perform conductor immunity using this EM clamp. Okay, so with this, I'd like to end my discussion. Okay, please up to like and subscribe. Once again, thank you so much for your time. I hope to see you guys soon. Bye for now. Thank you.